Spencer, you are mute. Mute. We cannot hear your voice, Sensei.
Okay.
Ay.
Sorry.
大丈夫です。
I forgot. I was late. Okay. So Zafira-san, could you start?
Can you see my screen, Sensei?
Okay.
So this week I'll try to apply 20 stories. So last time we discussed what if we try less than 20% for metallic damper. So this is for 2.5 meter wall length. So basically, if you can see here for first of all, 2.5 meter wall, the capacity is very low. And if you can see in this box, so the wall actually, the damping is only 5%, but because damper actually it dissipate energy, it have large damping, but when we have a low capacity metallic damper, the force is actually very small and energy is, if you can compare energy for metallic and the wall actually dissipate more energy compared to the metallic damper. So that's why it doesn't fit. And even if I compare with the time history and analysis here, this is under Kobe. So basically 2.5 meter wall doesn't fit with the criteria that we target. This is 2.5, this is 5 meter wall, and this is 7.5 meter. And like 5 meter is a moderate performance. So if we check the 5 meter wall, basically for metallic damper, it still doesn't fit with the target, even 100%, even though 5%. So 5 meter wall and 5% metallic. Yeah. Okay. We can see the metallic doesn't dissipate much energy compared to viscoelastic. Actually, viscoelastic this can dissipate more energy. For example, 20% and percent. Yeah, like 18%. But it also depends on because this is 20 stories, Sensei, so it's much more taller. And actually the length of the wall also influence the design. So for 20-story building, 7.5 actually much more better for the structure wall. So if you can see 20 stories, 7.5 meter with 200 viscoelastic, the energy start from 10% for equivalent damping. And then when we go to 40%, it works much more better.
Okay, could you show me 5% first?
5% under metallic. This one. This is the shorter wall.
Could you explain why this blue line is so high?
Okay, let me open the Excel 20 story. So from here, we have the target displacement. And then this is our equivalent damping. And from the target displacement, we can get our effective period based on the equivalent damping. So here is a 5%, and our equivalent damping is around 0.57. Yeah.
Equivalent damping is 5%. Oh, okay.
Yes, but this is 5% line. So
Mm.
then we can get the equivalent period 0.57 second, which is here. And then it will automatically calculate for this line. So this SD is our target displacement, and SA is our target
So could you
accelerations.
stop? So it means if you want to go down this line,
Yes,
what you can do is increase damping, right?
yes, increase damping.
Increase damping. Could you stop moving?
Okay, sorry.
So increase damping or increase capacity.
Yes, capacity. Either these two.
So this is a case coupling beam is very weak,
Yes.
only to 5%.
Yes, yes.
So it's very weak coupling beam.
And also very weak wall, 2.5 meter length.
How about 7.5 meter length? Any change in the
Yes.
line
7.5 meter.
on the 5% metallic damper?
I have to close this one. Here. The capacity is much more higher.
Higher because wall is larger than before.
Yes, yes.
Okay. And also damping is not 5%. Damping is now 12%.
Yes. But metallic is small because if you can see here, the energy here, beam energy is very small compared to the wall. So that's why the damping for beam actually is big because it's 5% and it dissipates energy. But the couple beam is very small and it doesn't have enough capacity, and the total energy release is very small compared to wall. That's why if we compare the percentage of equivalent damping is small here.
But this damping is almost, so wall, equivalent damping of wall means the wall is getting damaged, right?
Here is the ductility, sensei. It's still less than 5.
The lower part is more than 1.
More than 1.
Okay. Could you show me the 5 meter case?
5 meter. Okay.
Yeah. You can close this one. How much ductility factor for the column?
For the wall.
Yeah.
Okay. So the ductility for the
almost no damage. But the coupling beam has so much damage, especially upper floor.
The middle floor.
But the total damping is only 5%.
Yeah, 5%. And a little bit for metallic.
Little bit for metallic. Okay, so in this case, if you increase the capacity of metallic damper, maybe you can get a better result, right?
Actually, Sensei, like when for metallic damper, we know that 30% is maximum for the metallic to yield. So if we plot more than 20, for example, this is 20%, it start to yield. We can observe for the degree of coupling is 82%. When we increase from 40% until 100%, actually it's become constant, Sensei, because the metallic doesn't yield, so the performance become constant, like we can say 5%, 5%. But if we use viscoelastic, the actually performing is getting better and better and better from 200% until 1000%. Yeah. If you see from for example, we compare 200% the damping here, so it start from 22%, and then 40% is a bit less, and then but the total equivalent damping is increasing.
So let's think about the design procedure. Okay. So start, and first you should check maybe coupling beam ratio, beta CB. And if it's over than, for example, 80%, maybe you cannot use damper. And the damper is effective if coupling beam ratio is, I don't know.
In the range.
In the range?
Yeah. Last time we have, like in the previous paper that we studied, we can see that this depends on the high rise of the building. So low story building to mid rise is around 25% to 40%. And for high
from your result.
From my result is around this.
Yeah. So well, so we try to propose design procedure for coupling beam. And you have many results, right?
Yes.
So in case coupling beam ratio is more than 80%, actually not good. So not good. So there must be some range less than, I don't know, well, 80, more than
60.
Yeah. So do you have any data to prove?
Okay. For 20%, we can see the good design at 7.5 meter. So viscoelastic 400% actually is a good example. So like 85%, 83%, this one. And this is 70, is the good, if you can see here, the good is around 70% to 80%.
So in case of metallic damper, this range is maybe 80%, and I don't know. But in case of viscous damper, maybe this range may change.
Yes, Sensei.
So could you summarize your result?
Okay.
Which case you success to design, and which case you cannot success?
Okay, Sensei.
And it is very close. Could you show me, for example, one slide before?
One slide before.
So, for example, in this case, do do you know how to design, how to modify your design to be much closer?
One way is to increase the capacity, means that we have to increase the wall length.
No, we cannot touch wall length.
Increase the capacity, you mean the viscoelastic percentage? So we can increase the damping.
Do you have a result of 400%? For example?
This is 400 sensei. This one.
It's 400. Okay.
Yes.
How about 300?
300, I don't have, but I have 600.
400 is below the capacity curve, and go back. 200% is over. So it means 300% might be
Match.
right?
Okay.
So it means you can success to design by using displacement-based method.
Okay, sensei.
And this is a capacity coupling ratio is very large.
Yes.
So if you use viscoelastic damper, you can design even coupling ratio is very high. Okay. Okay. Let's see. Could you go back to metallic damper again?
Which length, sensei? 5 meter? 7.5. This is 7.5.
7.5 and changing this percentage.
Percentage,
Okay.
okay.
5%.
5%, this is 10%.
10%.
And this is 20%.
So these two lines not match each other.
Yes.
This is 5, 10, 20. And next one?
This one is 40%.
40%. Still, there is a difference.
The energy is very small, sensei. If we see this one, compared to wall, it's very small for the metallic damper.
So there is a kind of a dilemma. If you reduce capacity of metallic damper, it yields very fast, but energy dissipation, I mean, this area may not be so large.
Yes.
But if you increase the capacity, yielding not happen so often.
Yes. Only until 30% for metallic damper.
So it means energy is also small. So even you control the capacity, energy dissipation of the coupling beam is doesn't increase so much. So this is a kind of limitation of the metallic damper.
Yes.
And the viscoelastic damper, even small deformation, it dissipates energy.
Yes.
And if you increase the capacity, it will also increase damping.
Yes, I see.
Right? So it's easy to control. I mean, what to say? You can increase capacity and damping both together at the same time.
Yes, I see.
Okay, it makes sense. Okay. And did you try hybrid case also?
Hybrid case haven't yet, sensei. I only try metallic and viscoelastic. Yeah.
So hybrid case is necessary in case if you use the viscoelastic damper and increase damping force. Sometimes this damping force is too much.
Yeah.
And beam with viscoelastic in the middle, if the damping force this force is too large, the beam itself, I mean, other part of the beam will go enter nonlinear. Or supporting connection might be damaged. So to avoid this problem, we insert metallic damper,
Mhm.
for example, at the end of beam, for example. So this metallic damper has a capacity up to here. Okay? So below this capacity, viscoelastic damper in the middle will dissipate energy.
Yes.
But at the moment, this force reach capacity of metallic damper, the force cannot go over because metallic damper has a limitation. So this is an advantage of hybrid system. But the question is, how to say, do you have any case you observe such excessive, damping force?
For metallic dampers, I said.
Yeah, because you put, no, not the metallic damper. I'm talking about the viscoelastic damper.
Viscoelastic.
So you have a viscoelastic damper in the middle,
Yes.
and you know the capacity of beam
Yes.
attached to viscoelastic damper.
Mhm.
So suppose this capacity is QB, and this viscoelastic shear force is QC.
Mm.
And if QC is more than QB, this beam will get damaged. Do you have any such case?
Actually, when I notice and say between 80% and 100%,
No.
so we can see the capacity does for this box capacity doesn't change much, but if we can say degree of coupling, this is the good range for degree of coupling about 70. But when we increase the capacity more, like reach to like 10 times, the degree of coupling is become bigger. So can we,
So in this case, how much damping force?
about 23%.
No, this is this is a damping coefficient. I'm talking about the shear force of the damper.
It's about 29,000
Is it
kilonewton.
less than the capacity of the beam?
More than capacity. The 100% is 2,900 sensei. So this one is like 10 times.
Higher.
Yes.
But you, 待ってよ。you did take over. And you also do stress reader analysis
Yes.
by this 1,000%.
Yes, sensei. But for viscoelastic, it cannot use pushover, so we have to use formula to calculate the damping and the energy.
Yeah. But
Yeah.
in the next slide, you have a result of time history analysis.
Yes.
So this is 1,000%.
This is metallic. This is viscoelastic.
And you have a result of 1,000%. Could you also plot the graph of shear force of, maximum shear force of damper in each story? Maybe, I don't know. You can draw this kind of graph. Maximum shear force of the damper. And
I
you
have
can
question.
compare with capacity of shear force capacity of beam. Even you design 10 times higher than capacity of beam, the damper doesn't have some, I don't know.
effect. If we use, for example, this is viscoelastic.
Do you have the result of max damper?
This one is viscoelastic and inside have max spin. So the shear is this one. And this displacement is 0 because this is a pushover.
No, I'm asking about the result of time history.
Time history.
Max damper. Max beam? Okay,
Max
max
is-
beam. Max beam. Okay.
Yes. So this is the Q.
Is this a shear force of the damper?
This one is shear force and say Q. This is force. And I copy.
あ、そうか。ちょっと待って。
So this is the force. And this is the displacement.
Under 1.77. What does it mean?
This is ductility, sensei. UN.
Okay. But this is viscoelastic damper.
Yes, sensei.
Okay. Could you show me data beam?
Data beam. Here.
And
It doesn't show here, sensei, because this is for rebar. It doesn't show the capacity here because this is for rebar. This is data beam for viscoelastic.
why there is no data beam?
This is rebar.
Because it's a steel beam. Right? Because it's not reinforced concrete.
Yes, it's not
Really?
reinforced concrete.
そう。ちょっとこれは直した方がいいな。Okay, so what I worry about, you have a steel beam with viscoelastic damper in the middle,
Yes.
right? And the shear force of this viscoelastic damper from max beam, it is 100, I think, remembers 13 kilonewton, right? So I want to know steel beam is okay or not, elastic or not. You don't know.
Can we check on the ductility based on ductility sensor?
Okay, I will check Stella 3D and I will try to change this part. Yeah, because this beam has a, well, not cracking, but at least it has a yielding moment, right?
Yes.
And if you double yield moment and divide by length of beam, you can get the capacity of steel beam.
Yes.
And you can compare with this one and this one. And if this one is larger, it means this steel beam may yielding, may have damage. Okay. I will change this stress rigidity to you can get the MY.
Okay, Sensei.
Yeah.
Sensei, for the model, right? We actually use direct input, right? So we have the metallic spring and also the middle is viscoelastic spring.
It's a direct beam.
Yes.
Could you show me Stella program? Could you?
I will open.
Yeah.
So viscoelastic. For viscoelastic and even metallic, we use direct method because we want to use the single spring.
Could you show me the property of this one?
This is 1, and this is the capacity of the metallic beam.
Okay. You have a capacity here.
Yes.
2,900. And multiply 2 and divide by how much length?
Length of the beam is 3 meter.
3 meter. 3. So it's almost 1,000.
1.9.
So 2,000.
2,000.
And your shear force is 730 or something.
Yes.
So it's much less than the capacity. Okay. So even 1,000% of viscoelastic damper. Why you call this one 1,000%?
Actually, I just want to check the performance, which varies capacity for the viscoelastic, and I want to check at which percentage it performs better.
And 100% means
to 100% is same as here, 2,900 kilonewton. This is the capacity for 100 kilonewton, 100%. Let me open this one. So this one for viscoelastic. So this is 1,000. So 100% is 2,900. Same as metallic. So at metallic, 100%. 100% is 2,900 kilonewton.
Yeah. And so you assume viscoelastic damper has this kind of shape, and how much amplitude when you design? Yeah. So how did you decide this 50?
60.
60. How did you decide 60?
60 based on target displacement for viscoelastic.
Target displacement of viscoelastic. Target displacement. How did you decide the target displacement? And also, how did you decide omega?
Omega is based on the period of the building.
Period of the building. Okay, so what is a 60 then?
60 is target displacement for viscoelastic. So how much the maximum damper can displace.
But how did you decide 60? 60 centimeter, millimeter?
Millimeter.
Millimeter. But actually, from time history analysis, what you get is 730 kilonewton.
Kilonewton.
It's a big difference. So actually, the group is, I don't know, 700, this is, what is the unit of vertical axis?
Vertical axis kilonewton.
Kilonewton. So this is 10,000?
Yes, sensei.
10,000. This is 5,000.
Yes, 5,000.
730 means like this. So actual energy dissipation by time history analysis is big difference from your initial assumption.
But nice.
So how did you decide 60 millimeter?
This is like assumption for the displacement that will allow for this viscoelastic.
How did you get this value?
This is like a different assumption, like 60 centimeter.
Sorry, I don't understand.もうよくわかんないな。
I think for viscoelastic damper, they also have limited displacement. So we can put the limited displacement for the damper.
Mm. うん。And this C value is depending on the material of the viscoelastic
Yes.
material, right?
K and C is depends on the GE and GC.
So the capacity you're expecting, this one, is too high. Actual
Yes,
capacity is shear force is only 700. So I don't understand using this, I mean,
this graph.
This graph. What is the meaning of this graph? Yeah, omega might be okay. The question is 60 millimeter.
This one is supposed to be the maximum displacement for the viscoelastic itself.
How did
So
you calculate 60?
60. Actually, it depends on the device itself. How much we want to limit the displacement.
How much So how did you calculate 60?
We doesn't calculate. Actually, it's assume like how much limit that we want to put for the viscoelastic. So my limit is like 6 centimeter for the displacement.
Viscoelastic damper is a viscoelastic material, and it will deform by shear.
Yes. But it also have the metallic plate.
Yeah. So 60 millimeter means
6
how much
cm.
shear strain, and the damper can deform 60 millimeter.
Yes.
Yes. Could you explain?
The what I understand from the 60% is the limit for the damper to how much it can how can I say displacement by shear. So 60
Is there
centimeter
any
is
document to describe it about this?
can you repeat, Sensei?
Is there any document?
Document.
So height is this one, width is this one,
Yes.
and how much deformation this damper can deform?
It should be 60 maximum.
Well, how did you find this number?
This is fixed number. So we can change here. Like if, for example, we put 40, it will change here. And other data also change.
So how did you decide this number?
We can decide this based on how much we want to design the displacement for the damper. For example, I want to limit my damper displacement like 6 centimeter. So and then it will give me for K and M. And also it's based on the height and the width of the viscoelastic material. So if we put, for example, if I limit 40 centimeter, 40
So I
millimeter.
can put 100 or 200 here?
Yes.
Yes? Are you sure?
Yes, but it doesn't, if we put 100, it become very big. The forces become too big. So I limit to 16. So we can, it's not so much displacement.
Are you sure you can produce such damper?
If, let's check this.
So there must be some specification of the damper product.
In the Crystal Plus, it only discuss about the viscoelastic material. It doesn't discuss specific like the damper itself, because the damper that they use is the viscoelastic material. For example, this one, and the one that they use is different from that we use. They use only this. They only study about viscoelastic material.
So you assume this damper can deform 60 millimeter.
Yes.
Are you sure?
Yes.
What kind of viscoelastic material? How did you decide C value?
C value based on this. C value based on the formula. And here, this is one from previous paper. So they have 3 different material.
Yeah. So this is the property of the viscoelastic material.
Yes.
So how much shear deformation it can deform?
So the force is calculated by this one, this formula. So when we have the material value G, E, and GC, including omega, and then we can calculate K and C. And then from here, we can substitute in this formula to get the force.
But if you deform the damper, it will be broken, right? Finally.
Yes, that's why we have limited displacement.
So where the, I mean, in the catalog of my product, there must be limited deformation.
In this paper, Sensei, it doesn't put limited displacement. They only give
Yeah,
this.
but you cannot put any number here.
Can we use the existing catalog with the maximum displacement and apply to here?
It depends on the product.
Yes, Sensei. But previously, even from the company that we saw, they only have viscoelastic wall.
But you have this
This,
value. And you have a picture of this material, right? This damper.
okay, I will check again, Sensei. This paper.
Okay. So we must check one by one without any, なんていうのかな。Let's say, without any evidence. We must decide based on the evidence. Okay? So 60, if you put 60, you must give me the evidence why this value is 60.
Okay, Sensei. So like for now, we only have 3 different story, 10 story, 20 story, and 15 story. Now Sarah is doing 15 story. Yeah.
Dr. I know you did many analysis.
Yeah.
If you make a mistake in the beginning, you must do everything again.
Okay, Sensei.
Beginning, starting point is most important.
Right.
How to decide damper property and what kind of viscoelastic damper. It's most important.
I will find the missing puzzle and show it to you. Okay.
The procedure is okay, but
Okay.
starting point is a little bit vague.
Okay, Sensei.
Yeah, for me. Okay, so who is the next?
I think I am.
Sarah-san, okay.
Okay. This presentation is about metallic and viscoelastic damper with the 3 types of wall. That was 2.5 meter and 5 meter and 7.5 meter. And for about metallic damper 5% is target blue line obviously is over capacity curve. This one. This is 15 stories. And for about 5 meter, this is no, for about 7.5 meter in here.
Okay, so this is the same result Zafira-san show me.
Yes.
Mhm. Mm.
For about viscoelastic damper in here, that one,
Mm.
this one.
Mm.
This is wall 2.5 meter.
Mm.
And this one wall 5 meter.
Mm.
Yeah, almost same.
Mm. Mm. Mm.
Yeah, and that all designs of the viscoelastic dampers result don't have big difference. Sensei, can you hear me?
Yeah. So what is your summary?
Uh, uh, yeah, that's it. But I want to check the time history, but
Mm.
in here,
Mm.
this is under the copy of wall 2.5 meter, but
Mm.
yeah, but almost same.
Yeah, because metallic damper is not yielding. So if you change the capacity 40, 60, 80, 100, damper is not yielding. So all results are same.
Yeah.
Mm.
Did you also do for other wall, Sarah-san? Only
Although-
for 2.5 for the time
Yeah.
history analysis?
Yes.
You should compare with other wall too. You cannot only compare with one wall. So maybe later you can compare with other different wall, so you can see the different performance.
Oh, I see.
So anyway, after you try many analysis, finally you must summarize
Mm.
out and make some story or design procedure. Yeah?
Okay.
So yeah, right now you did many analysis, but we must propose design procedure so that the designer, don't need to do many analysis. If designer follow the procedure directly, he can get a good, design.
Yeah.
But so far, you must do many analysis to find the best one. But please think about how to get best design. So start from starting which factor. For example, coupling ratio might be one factor, or I don't know. So in case you do, so bottom part is a displacement based design.
Yeah.
I think this one looks good, but you can make it more closer to line.
This one too.
Yeah, you can make it more closer, maybe. But how you can control these two lines? By changing the viscoelastic percentage?
Yeah.
Yeah, maybe. But for metallic damper, even you change the percentage, the result doesn't improve so much. So,
For example, for this 7.5 meter, if I increase this decrease this percentage, it will be closer with the capacity curve.
maybe.
Yeah.
Yeah, yeah. Okay.
Yes, that's it. That's it.
Okay, yeah. Ataya さん。How are you?
こんにちは、先生。
How was your
Thank you.
internship?
It was good, 先生. It was good.
Oh.
Good and new experience for me, 先生.
And you think the company is, I mean, one of the candidates you apply, you work?
I don't think so, 先生, because they didn't look interested.
Oh,
Yes, 先生.
okay. But you must find a company to work in Japan.
Yes, and so I'm looking, I'm searching.
So the company you went for internship is not a good company.
No, for me it is okay, but they didn't say something about.
Oh, really? Oh. Okay, okay.
Yes. May I share the screen, Sensei?
Oh, you have anything to show me?
Yes, Sensei.
Okay, please.
Sensei, if you remember at the last meeting that I had, there was a problem with the model when we inserted a small value for stiffness and damping of the TMD. The result was very good, which was not correct. So during this week, Soronya-san gave me a model, and he used the damping proportional to stiffness and mass, both of them. The third one. So when we use this damping factor, the damping type, then the displacement does not decrease a lot. So it means that the result is okay. Yes, Sensei. But I don't know the reason why involving the mass can change the result too much.
Yeah, I don't know the reason also. Interesting.
Mm.
So we
Yes,
should
sensei.
select number 3, ready dumping.
Yes, sensei, it is number 3. Yeah.
Okay.
Yes, thank you, Saranya-san. And I just started nonlinear analysis with this model. One story. I analyzed linear and nonlinear, changing this to shear spring and flexural spring. So the time period of linear and nonlinear is different. In this case, linear is a little higher than nonlinear. So the value for stiffness of damping is also smaller. And when I compared the result, installing a TMD decreases the displacement by 24%, but in the nonlinear case, it decreases about 44%. But it is obviously the displacements are higher because the model goes to the nonlinear range. So I don't know if it is true for the other models or not, but it needs a lot of analysis for other models that just I'm looking to find a very nice, good arrangement of multiple TMDs to control the non-linearity of the model also, sensei. And that's all.
So nonlinear means the main building go enter nonlinear.
Yes, sensei, this
Well, it depends on the input, earthquake.
input is El Centro here, the same, sensei.
Oh, El Centro.
Yes, sensei, the same for both linear and nonlinear.
But how about another earthquake?
I didn't apply yet, sensei, because of the time, so I just recently.
So how did you get this value?
This is gave me the steroid, sensei. I just only designed a column and a beam with these properties. So when I analyzed without TMD, so the period was given here.
But it's an elastic period.
But when we change, sensei, the non-linearity and linearity, again, that T also change. It doesn't depend why it's changed.
Okay. You misunderstand.
Okay, sensei.
Because how to say? Could you close this window? Okay. No. Show me the slide.
Yes, sensei.
So if you design TMD, I cannot draw. Why? I cannot draw. Okay. Now I can. Okay. So how to say? The beam with elastic, and this is a beam with nonlinear spring. Okay. And
Yes, sensei.
well, なんていうのかな。This one is you neglect nonlinear spring. So completely elastic.
Oh,
And,
okay.
this one is nonlinear spring, but elastic range and nonlinear range. Okay.
It is an average, sensei.
Hmm?
It is an average. average of this Lagrange and Lagrange.
This is, I mean, ideally it is infinite stiffness, but the computer cannot treat infinite. So it is very large value,
Okay,
elastic
Sensei.
range. And if you calculate period, how to say, they calculate period using this elastic stiffness. So this is this value. Okay. So this, in linear case, period is a little bit, oh, no. This is longer. This is shorter.
Yes. In this case, it is longer, but
ちょっと待って、なんかおかしいな。Something wrong.
Sensor, this may be because this is only one story structure, so maybe the nonlinearity is not having much effect. I don't know.
Yeah, so if you design the TMD on TMD, and this main part is nonlinear, right?
yes,
So in this
Sensei.
case, you assume some inelastic deformation, or some deformation, maybe up to design target by pushover.
Yes,
Then
Sensei.
you calculate equivalent stiffness from bottom to here,
Yes, Sensei.
equivalent stiffness. Then you calculate equivalent period.
Yes, Sensei.
But in your case, you didn't do any pushover.
Sensei, may I share another? Sorry, Sensei, just a moment. Since I tried this for just one story,
Oh, okay. Very good. Yeah.
so maybe, but for multi-story, I don't know if it is just I use this value, QI, which is the shear force of the story over the weight of the building. And this is the delta, this is the displacement of the top story to the height of the building.
Yeah, so if you draw capacity spectrum by pushover, you can get the same card, very similar one.
Say that, and I was thinking to design 3 TMD for each of this.
Okay. Yeah.
And then analyze what happens.
Yeah, it makes sense. Yeah. Okay, please try this one.
Okay, Sensei, thank you.
So even multi-story, if you do pushover by Stella, you can get a capacity curve. It's equivalent to 1 degree of freedom, something like this.
Okay, Sensei.
And you can get the equivalent period.
Yes, Sensei, I will.
Yeah. So if you want to control the first mode, you can use capacity curve. Yeah.
And Sensei, I
Okay.
have a question, Sensei, and in this case, it is released all the X direction. But in some cases, if I consider releases all the X direction freedoms, then this beam which is under the TMD will fail very soon. Because in reality, we will have a lot of beams under the slab that support the is the TMD weight, but in
Mhm.
this model we cannot do that. So
Mm.
the weight of the TMD concentrate only on the beam. So may I use only, for example, 2, 3, 4, 5, 6, only X direction, sensei, one direction? The result is reliable or not? I don't know.
In this case, beam, yeah, you can do it. You can do it. Yeah, it's also okay.
Okay, sensei.
No, 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 no. You, you need 5. You need 5. Otherwise, the beam cannot deform.
It means that 2, 3, 4, 6, 7, 8.
6, 7. Yeah. Well,
Okay.
actually, 7, 8 is always neglected. So you can just 2, 3, 4, 7 is enough. 2, 3. Okay. Yeah. 2, 3, 6, 7. Maybe that's enough.
2, 3, 6, 7, sensei.
So what do you want to do? You want to
When
avoid damage of beam?
analyze, sensei, and I inserted 2, 4, 7, 6, 7, which means that the X direction up and down, also in the 3 directions, Z, X, Y, and all. No sense. In X direction, the sway, the flexural is free. So when I put the TMD on the beam, the weight of TMD on the beam, this beam fails very soon, sensei, because the weight is too much, weight of TMD.
But in reality, also TMD force is on the beam, right?
Yes, sensei, but there is a lot of, we can consider a lot of beams and the weight is distributed, but here it is not distributed, I think.
But the weight is supported by the column.
Maybe I will consider the, no, the first, the beam transfer to the column, sensei.
Sorry, I don't understand.
Sensei, the weight of TMD is first, it is inserted on the beam, then beam transfer the weight to the column.
Weight is concentrated on the node only. There is no weight in the middle. Why beam can deform by weight?
In this model, it's okay, sensei. But if we consider like this, there is no beam. This joint will fail very soon, sensei.
Yeah. Of course. There is no column.
Yeah, because of that, it is. I wanted to consider only.
Yeah, but if you no, in this case you should なんていうのかな。
Sorry, sensei. Maybe I should work only on the top, not in the middle. At the first.
Okay, so in this case you should use top story is rigid floor.
Yes, sensei. And for example, I can install many TMD on the top like this. For example, on the in here there is frames
Uh-huh.
like this, sensei. All the nodes have column,
Mm.
and I install, for example, 2 TMDs. If it is wider, I can install 3 to 4 TMDs also, sensei.
Mm.
In this case, the weight of both TMD will transfer to columns directly.
Mm. So what is the problem?
The problem is, sensei, if we, for example, if we have a 10-story
Mhm.
and we install one TMD on the top floor and one TMD, for example, in the 7th floor,
Mhm.
so we need to use like this to install the TMD in the middle.
Anyway, please design the building, and we can discuss later.
Okay, sensei.
I don't understand what you're talking. So please show me.
Okay, sensei.
Oh, yeah.
Thank you, sensei. And that's all.
So okay. Anyone has any presentation today?
No, Sensei, I don't have anything. I'm writing the paper for the MDPI journal. So,
あたやさんとザピラさん、
はい。
そっか。You must make a presentation at the JES next month.
Yeah.
But after you get the program, we should discuss about the accommodation and travel schedule. Okay.
Okay, sensei.
And next week, I forgot to tell to the students at the lab meeting. There's a meeting with Sumitomo Riko Company. Do you remember the date?
yes, since 11th.
11.
It's 11:10 o'clock.
Yes,
Yes.
okay.
So, Zafira-san, could you prepare short presentation
Yes, sir.
for this?
I will send today. Already prepared some.
Can you show me now or later?
Later, sensei.
Later, okay.
Do I have time today, sensei? Or maybe I just open here. Okay. Oh, not this one, sorry.
Mhm.
So basically, I introduce what we are doing. We are doing a type of structure wall, and so they have a different type, but we are focusing on couple shear wall
Mm.
and the force distributions, and then how we determine the performance of the couple shear wall system,
Mm.
and then a type of device that we apply for the building to dissipate energy
Mm.
to improve the performance. And then this is the formula we calculate for the equipment damping,
Mm. Mm.
and then the research objective.
Mm.
So
Could you prepare many information about the viscoelastic damper?
this characteristic damper.
Yeah,
Okay,
this
thank you.
middle one. The size and what material
Mhm.
and the limit deformation we discussed before.
Yes, sir. Okay. I think
Because
that can-
we try to ask Sumitomo Riko Company to produce viscoelastic damper. So they want to know more about this
device. Okay, Sensei.
Yeah. Okay. Okay. So then we want to visit the Sumitomo Riko company. I'm thinking to go there in November, middle of November or end of November. But Saraya-san, you leave October. そっか。
Yes.
October ね。うん。26 or 27 October, I can go there.
Sensei, I think Saya will leave 24th. No. When you will?
No, I'm here that week. I'm available. I will go next week, 31st October.
I see.
Saraya-san, which date you leave Japan?
Sensei, I leave Toyohashi on 30th October, Monday,
Okay.
and I have my flight on 31st October from Narita Airport in Tokyo.
Okay. What, so 26 or 27,
Yes, Sensei, it's
you
okay.
can go to
Yes.
Sumitomo Riko.
27 is good for me, Sensei. If
So Zafira-san, you prefer 27.
yes, 27.
Okay. 真島君は27日ってどう都合は。
27日は大丈夫です。
大丈夫。
26も大丈夫です。
じゃあ27でちょっと計画してみるか。OK。OK。OK, shall we finish?
Sensei, we should discuss next meeting.
Next meeting. But 11 anyway, 10 o'clock, we discuss with Sumitomo Riko. Then after that, えっと、18、19。20, I'm available next week, Friday.
Yeah, I'm okay, Sensei.
So shall we have a meeting, let's say, same time, 1 o'clock?
Okay.
Okay? 20.
はい。
はい。じゃあ、let's finish.
先生、いいですか？画面共有して。
はいはい。
試験体のやつを報告だけ昨日見せられなかったので、
はいはい。
今 CAD 見えますか？
はい、見えます。はい。
この真ん中が試験体で、そう、これは振動台の中心に置いていて、その周りに青い鉄骨、もう西松にある青い鉄骨フレームを置いて、レーザー、モーションキャプチャーはこの滑車のこの側面に、全部、左右対称に、全部で14個してる予定で、加速度計も各層に置いて、レーザー変異系は、ここの右側のフレームと試験体の幅が今600ミリで、レーザー変形の基準距離が500なので、まあ、計測範囲プラスマイナス250でギリギリ入るので、この右側からレーザー変形を置いて、このかさ上げ台の側面ぐらいを狙って計測しようかなと思ってます。
いいね。かっこいいね。
どうですかね。他なんか、あれ、考えないといけないことありますかね。ワイヤーの配置はもう一回解析して最終的に決定しようと思ってます。
何パターンぐらいやる予定なの？
なんか山崎さん的には昨日の夜に工程表が送られてきてましたよね。先生見られました？
結構日にちがあったね。
これ今、PDF 見えてますか？この青い番号で0123456789で一応10個あるんですけど、わかんないです。なんかここで一時中断、2月の真ん中一時中断して合計7ケースにするとかって書いてあって、まあ、やれるならたくさんやりたいんですけど、日数決まってからって感じです。あと、なんか今、告示波だけでやる、なんかような感じなんですけど、それだと工事モードが出ないって、昨日のゼミでおっしゃってたので、JMA 神戸を追加したいんですけど、まあ、それは解析やってから、週末やって次の10日の打ち合わせまでにもうちょっと整理しようと思ってます。
一時中断っていうのは、みんな忙しいってことかな。
いや、多分山崎さんがやりたくないっていうか、山崎さんの気分だと思います。
ああ、そう。
3月1日から、振動台はもうメンテナンスに入るんで、片付けは絶対2月中に終わらせないといけない。で、まあ、実験自体は2月いっぱいできるはずなんですけど、宮崎さんがその領収書の整理とか、まあ、
そうだね。
いうのを
それはね、はっきり言うと、まあ、ここで一時中断って書いてあるあたりで本当終わった方がいいので、最後の7、8、9は、実験なしの方が本当はいいかな。
ただなんかここでやめてしまって、次いつか、なんか、いつになるのかわかんないよりかも。
でも試験体は、まあ、保管してもらうからさ。
はい、保管はしてもらうんですけど、翌年の1月、2月とかになっても、もう多分僕、白露も終わってるし、なんか、やるんだったらもうこのタイミングで
えーっと、
やっちゃいたいなっていうのは個人的にはあるんですけど。
うん。うん。まあでも、
さっきの、あれでしたっけ、西松じゃなくて、安藤はの三浦さんのメールでは、月火水木実験4日間連続やって金曜日、予備日ぐらいでもいけるんじゃないかっておっしゃっていて、それだと、例えば、5、6、7、8連続で実験して、13、14、15、16連続で実験したら、ここで8ケース終わらして、19、20は予備日に置いとくとかすれば、まあ、早く終わらし、日程的には早く終わるんですけど、実験ケース的には同じだけまあ、そこは10日の時に相談しないといけないんですけど。
今実験間隔が1日とか2日空いてるよね。
はい、ただ、三浦さんのメールでそんなに必要かって開ける必要が。
いや、俺もね、なんか毎日、それこそ1ケースずつやればいいんじゃないかなとか思っちゃってね。
はい、僕もそう思ってます。
うん
朝、暖気とか試運転して、実験、過信自体は10回したとしても1回1分なので、1時間あれば過信は終わるはずで、その後、例えば3時ぐらいからワイヤー張り替えても、5時までには、もう終わると思ってるんですけど。
それがいいんじゃない？
で、早く終わらせた方が。
それがいいと思うよ。いや、前倒しで実験ちょっと詰め込んどいて、後半ちょっと予備を入れとくぐらいがいいんじゃない？
そうですよね。
まあ、10日の日にじゃあ、相談しようか。はい。はい。
はい、それだけです。
あとは何に相談するかな。
もう一ついいですか？
はいはい。
で、ワイヤーの貼り付けるのを誰がやるのかあんまよくわかんないので、割と複雑なので、なんか建物模型を、ボビンとか木材で作って、それ見せながら説明した方がいいかなと、個人的には思ったんですけど。 実際にやるときに。どうですかね。
ああ、模型。
はい。滑車が多いので、ここの番号とここの番号に取り付けて、次、この番号に行ってっていうのをした方が左右両方で、左右っていうか、手前と奥で、
うん。まあ、そんな精密な模型じゃなくてね。
はい。単純に
うん。
なんか木材とかで
うん。
やってもいいかなって思ってたんですけど、
うん。
実験室にあるじゃないですか。なんか、公開講座用みたいな、ああいう、あれの小さい、
あ、そう、段ボール重ねたぐらいじゃダメなの？
そこは何でもいいです。滑車の部分だけがちゃんと、
下の部分だけあればいいんだろ？それこそ
はい
本物のボビン、小さいボビンを、こう、
はい。
接着剤で貼っつけておいてさ、ワイヤーを貼る話だよね。
そうです、そうです。
うん
100円とかで売ってるやつで作ろうかなと思ってるんですけど、どうですか？
あった方がいい。まあ、確かに間違えるとあれだからね。うん。
の方が意思疎通がしやすいかなと
う
思って。
ん。まあ、あるいは大きな模造紙みたいな紙に絵で描くか。
あれを9連書くのが大変なんです。自分でもわからなくなるぐらい。
ああ、
多分手でやった方が、ここワイヤー重なるとかが
あ
わかりやすいかなって思ってます。
あ、ああ。じゃあ、同じ模型を使ってケースごとに一回その段取りみたいのを説明するわけね。
はい、午前中その振動台暖気で使えないので、どうせやること多分ないんです。その時にその試験終わった後のワイヤー張り替えがあるんで、
うん、うん、
その前に1日1回相談すれば、
うん。あとはうちの学生でやるからだな。うん、
そうですね。吉井君を連れて行くかです。
うん。うん、わかったわかった。まあ、それは、あった方がいいと思うよ。うん。
はい、わかりました。
大変かもしれないけど。作るのが。
失敗するよりかは作った方が。
そうそうそうそう。うん。そうだね。じゃあ、いいかな？じゃあ、終わりますか。
はい、ありがとうございます。
Okay. So, that's all. See you. Bye bye.